I'm Rachel D. Nabors, and I wrote this talk because I was attending conferences uh, that were, especially in London, where I hail from, many conferences about AI. They throw acronyms around, but when you actually talk to the people in the audience, and say, "Do you know what a RAG is?" People are very shy to admit, but it's true that most of them don't. They hear the acronym and they may form an assumption, but they don't really know what's being discussed. And so this talk is to hammer out exactly what we mean when we talk about AI in the modern setting, and to demystify all of the acronyms, etc. Is anyone in the house a web developer? Yay! Do you use React? Well, if you use React.dev, you may recognize me from React.dev and React Native.dev. Those were my pandemic babies. I worked on the React core at Meta. I'm an American in London. Um, and because front-end development is kind of maxed out, last year I spent 2024 learning about AI using the Big Green Book. Does anyone own this book? Okay, I see some nodding heads. That's good. I understand your arms are tired from all the snacking. Um, I like to say this is the best 60 pounds I've ever spent. It has been the topic of some of my most popular TikTok videos with me trying to explain algorithms with whales. Believe it or not, actually a very apt metaphor. Uh, but before my big tech career, I made comics for teenage girls, and thus I will be doodling a lot of the things you are about to see. These are not AI generated images. I drew them on my iPad. I co-authored this talk with Claude and a couple of interns in the Bay Area. And because I like the way Claude talks to me more than ChatGPT, I'm going to be borrowing them to stand in for foundation models. What do I mean? When I say a foundation model, whenever you see Claude there, you can assume I'm referring to Mistral, ChatGPT, Gemini, Llama, which is not pictured because Meta does not give its open source projects enough money to hire logo designers. I'm sorry, Meta, I can't use a screenshot of your GitHub alongside the other foundation models. But when you see Claude, Claude is standing in for these guys as a general concept. All right, let's see. So the goal of this talk is to front load any missing pieces or recap any missing pieces you might need to get the most out of your time here. We're going to go over the evolution of narrow AI towards artificial general intelligence, or AGI, uh, how neural networks underlie deep learning, what a GPT actually is, and different ways to teach a model. And lastly, what vector databases and embeddings really are and why they're so dang handy. If this feels too junior for you and you want to go to another talk, get up and leave now. I will not be offended, but you will offend me if you do this halfway through and cause a disturbance. So you've got just a minute now to run. Okay, with that said, let's get started with our definition of AI. That's okay. You can go. I will not be. Oh no, you're sitting down. Oh, the pressure is still on. All right, let's get clear on what artificial intelligence means. I went to London Tech Week and it was AI this, AI that. AI was going to change so much. I didn't see an equation in sight. I don't think people know what they mean when they say artificial intelligence anything anymore. It means different things depending on who you talk to. But right now, there are two camps. Oftentimes, when you say AI, people are thinking foundation models like our friend Claude. And specifically, they're thinking of generative AI, although they might not realize that in this context, they are generative, as opposed to other AI models. If you were in Christoph's talk earlier, there are many different kinds of models. They are not all generative, but usually people, in layman's terms, are thinking of them. But then there's also artificial general intelligence, which is the kind of AI we think of when we think of science fiction or, I'm sorry, Dave, I can't do that for you. Whenever we're thinking of an intelligence that would be on a peer level with humanities. There's still some disagreement about artificial general intelligence's definition. We like to think of it as human, but there's still debate about what constitutes AGI, when it will arrive, and what it will be capable of. But there's some general consensus that it should be able to transfer knowledge between domains, possess common sense reasoning, is this a bird? Should not be a question that it would be asking. Learn from very few examples, the same way a small child is able to determine that, if a if an object falls on the floor and it's fragile, it will break. And then they're holding, a fragile plastic toy or a fragile glass. They should anticipate what will happen if they've seen one thing break, what will happen if they drop another. Most models couldn't do that today. Handle uncertainty and novel situations. I fail at that one, so I'm not sure if that is a fair definition here. And lastly, understand context and nuance. I definitely fail at that. I figure this was written by neurotypical people who never experienced autism, because some of these, I think, are questionably members of our definition of human intelligence. There are many ways of being intelligent. But here are some things that we assume often are components of intelligence as we know it, but artificial intelligence may lack. For instance, being conscious or self-aware. Trees, for instance, are able to communicate with each other, yet they lack our definition of consciousness. They communicate via chemical receptors and chemical phenols. They are able to tell one another and react. Many species are able to react and communicate with one another, but do not possess a central nervous system or are able to prove their consciousness. They may not think or reason the same way that we do, or arrive at conclusions through the same methodologies. We've made many greater strides in our quest for AI by abandoning human-based models of cognition and just trusting heaps and heaps of math. And of course, it definitely may not have emotional intelligence. If you think of Data from Star Trek, who's obviously an imitation of autistic human beings. So once again, I feel like this might be a biased definition, and we can question whether some of these things are really it's a very not just anthrocentric, but also modality-centric way of looking at intelligence. So what we currently have, it's narrow AI. It does one job really well: playing chess, identifying cancer, finishing your sandwiches. Um, of course, AGI would be the next step, which would be making decisions, doing multiple things at once. All of the discussion points I just hit. But then, of course, there's super intelligence, which is doing things better than we are at doing it. Could you imagine, for instance, merging the large network that trees are able to exhibit, where they're able to communicate with each other across mass expanses of times, cross-clonal copies of each other, um, and combined that with, for instance, a reasoning model and the ability to speak? That would be arguably superhuman intelligence, to have that many creatures in sync thinking together. So anyway, yeah, that would definitely be capable of competing with us for dominion over the planet. So yes, bad things, possibly. So let's take a look at how we got here. We're going to have some bonus acronyms. We've been marching through AGI, but where did it start? It actually started all the way back with something called the perceptron algorithm. All right. And this is what perceptron looks like manifest in the physical world. This is what is it? The Mark I perceptron there. So the perceptron algorithm it was the first machine learning algorithm. It was designed to mimic how a biological neuron works. It was first described in 1943, and it wasn't implemented until 14 years later. Wow, things have certainly accelerated, have they not? And yes, it was built into the Mark I perceptron machine. Its first implementation. Now, there were claims that it would be able to reproduce itself and be conscious of its own existence, which were overhyped. It was capable of proving that machines could learn by example, that they could update their own code based on input from the outside world. But its hype coincided with the first AI winter, which was very unfortunate for poor little Perceptron. The rumors of its nature were greatly exaggerated, and Thus, it was let go into the annals of history. So here we go. Let's talk about let's talk about how perceptron actually works. Is a retina. Retina, not unlike the cells that you have in your eyes. They are stimulated by light, and this causes them to send a signal um, all the way to a layer of A elements. This is where we get the word layer from. And there's some math that happens, which I promised no equations in this. I should have said there will not be equations in the description because I feel like you guys came for equations and I am disappointing you. I see you nodding. There's the door there. You know what to do. Anyway, so each input had a weight or an importance, allowing you to tweak. For instance, the inputs in the center here might be given a higher importance than the ones on the outside, indicating how much light is falling directly on the retina surface. And then it added up all the weights of the inputs. If the sum exceeded its threshold, ultimately the system will output a 1. If not, it'll be a 0. Oofed. So note that single layer. This is very important. Um, this neuron design, it turns out that if you start layering them, a bunch of perceptrons, and you start stacking them very deep, and letting them pass that information to each other, you've formed a neural network. Anything less than 3 layers is a shallow neural network, but here you can see we can stack them incredibly deep, and that's where we get the deep from deep learning. It's about how many layers that you're stacking there. Deep learning is a subset of machine learning. There are other ways machines can learn, but we're working towards talking about foundation models. So we're going to keep following that track with deep learning. And I spent last summer also reading this cute little book, which I highly recommend. If you haven't built your own neural network, I highly recommend you give this book a read. It's a lot of fun. It's a lot of math and Python. But anyway, these networks are quite good at pattern matching. They need a lot of data and power to train, but the good news is it doesn't really need structured data. This is something that I think can be forgotten when we're talking about AI. AI needs data, it needs structured data. Not all AI needs structured data. Sometimes it just needs an entire internet's worth of data, and it can find patterns in there. But I do recommend if you're going to work with any diligence in AI, or if you just want to know more about how it works, doing the exercises in this book doesn't take that long. It's a lot of fun, and it will 100% ruin the magic trick for you when you're talking to Claude. So it's not magic. It's a lot of math. You might, like me, when I looked under the hood of React, have found out that it was just a lot of jerry-rigged JavaScript that was not very performant. I was like, oh, that's sad. Well, you know what? It is. It is kind of disappointing. But a lot of small things working together can be very powerful. Let's take a look at how deep these networks have gotten. AlexNet in 2012 was about 8 stories tall. Well, that's if you can visualize that, it's the height of a single story home, right? We're going to use buildings here. Then VGG 19, the 19, even though it came out in 2013, is for how many layers it had. You could imagine it as the height of an office building, perhaps this hotel. No, this hotel is only 8. Okay, 2 of these hotels stacked on top of each other. Then we had in 2015, we had ResNet, which is with a 50 in it, stands for the 50 layers deep it is. But Google's Palm clocks in at 118 layers deep, which is the size of a skyscraper. And GPT-4, it was about 120 layers deep. We don't have any evidence that going deeper than 120 layers improves the model exponentially, maybe linearly, but we're only seeing minor gains from continuing to increase the depth. In fact, sometimes we find that making the models deeper actually decreases their ability. Maybe it's like they're getting senile. They have too many connections and they're losing their connectivity, as it were. Has anyone watched Arrival? Yes. If you haven't watched Arrival, this is a great summer movie, beat the heat. It's a science fiction movie with no guns, nobody dies. But it's also the science fiction movie that made me cry on a plane. I have a weird sentimentality. But the interesting thing is that the arrival actually inspired a new kind of architecture over at Google Brain. If you read the paper, All You Need Is Attention, that architecture was inspired by Arrival. The idea was that it would be a neural network designed to decipher long sequences like musical notes or video frames or even speech. In this case, the person in the center there has to decipher what the writing, the circular writing means. That's the whole movie is a linguist. And so folks at Google Brain were like, I bet we could build a tool that would have that movie have a very different storyline. Nowadays, I'm sure they'd be like, oh yeah, we took a bunch of pictures of this writing and we put it into a model and we found a pattern. It would have a very different climax. So yeah, transformers, they break sentences into tokens, which are words or groups of words, songs into segments. Here's all you need to know about tokens versus parameters. If you're a layman like myself, when I first started getting into AI, I was constantly mixing them up. What is the difference between these two things? I'm used to JavaScript. I am not used to tokens and parameters. So, tokens. What's a token? Well, they're pieces of input you feed into a model. Models do have token limits. This is called the context window. GPT-3, for instance, only could take about 4,000 of these tokens at any given time. So if you were like passing an essay, you might pass in about 3,000 words. They usually have a ratio of like 3 to 4 because one word can, or it might be the other way around, forgive me. One word can be broken into multiple tokens, and sometimes two words become a token in and of themselves. So there's usually a ratio there. So you can say that that's about big enough for an essay. And then there's parameters. The parameters are the model's internal learnings. They're baked. They're kind of like your bones. While you're young and you are growing, you can pick up many languages easily, and your bones are flexible and they mend quickly when they're broken. But then when you're an adult, you don't learn new languages quickly. Your mental model of the world is pretty baked. I'm sure if we were able to put people on different planets and study how it changes their growing up, we'd find that children placed on another planet probably adapt better to the gravity and the oxygen than the adults. And models are kind of the same way. When you're training them, you can change these internal parameters because it's in the process of learning and baking. But then once it is produced, it's much harder to make those edits unless you like rip it open and start modifying its weights, which is kind of like plastic surgery. But I have a lot more pretty pictures to show you, so I'm going to stop with that model of metaphor. So parameters are the internal learnings. They're fixed after training, and they are measured in billions. So GPT-3, which has that tiny 4K window, it's got like 175 billion parameters. They're massive. You've got this Death Star with a tiny little port for getting things in and out of it. Itty bitty. All right. So turns out GPT, which we've been talking about, stands for generative pre-trained transformers. They are transformers that have been trained on the generative pre-trained transformer model, which means you pre-train them, they've got their parameters baked, and they're able to create new outputs given an input. You put things in, you get things that it's generated out. And here is, let's see. Oh, yeah, I just said all that. Beep, beep. Whew. All right. So that's right. These foundational models are just massive generative pre-trained transformers that have been trained on the internet, huge amounts of text. It's very interesting to read about how ChatGPT went from taking in very clean and very carefully curated content in its version 1 and 2 to finally just the floodgates opening and the entire internet being fed into it when when GPT-3 was being trained. Kind of creepy too. It takes a huge amount of content to train these suckers. They're very expensive. All right, so for the layman, oh my God. Sam Altman has said we've achieved AGI, but I think we're probably a lot closer to here when it comes to the march towards AGI. We've created something that's very good at showing us what we want to see. The contents that GPTs generate tend to be remixes of already existing content, not necessarily new content. And one could argue that artists are just remixing and rehashing older ideas. Everything is a remix, nothing is new under the sun. But for GPTs, that is doubly so. The contents that they create, uh, they are very good at looking intelligent. This is Alan Turing, who is World War II hero, gay icon, poster boy for AI, and the namesake of the Turing test. He was a member of he was in the UK, and he was a member of the team at Bletchley Park that worked so hard to crack the German, uh, the bomba. Anyway, God, Enigma. Thank you. The Bomba was the decoder, the Enigma. Yes, I know. It's shameful that I'm here in München and I forgot that. All right. But anyway, we actually don't know a lot about him compared to other people in the same space because a lot of the work that he was doing was classified at Bletchley, and it's only becoming more public now. Every year, Bletchley Park, which is a museum you can come visit if you ever come to London, every year they have more and more on display as they're able to share more and more of what the people were doing. It turns out there were tons of women doing incredible work with math, etc. But um, after the war, they just had to go back and get into the kitchen. So, oh, London, oh, England. So, let's get back to the imitation game and Turing. So, where a machine's intelligence is based on how difficult it is, in the particular test, a machine's intelligence is gauged based on how difficult it is to pick it out from a blind test against humans. Which, when you think about it, it's also called the imitation game. It is it's about how much you can get artificial intelligence to imitate a human. That's not necessarily a good predictor of intelligence. It's a good predictor of manipulative ability or deviousness, perhaps, but it stuck around. And this became the new benchmark. I should also take a moment here to mention that sadly, Mr. Turing is deceased in thanks part to the UK government trying to make him not gay. Uh, Now, I always like to include a 30-second moment of silence for the marginalized folks who contribute to pushing the state of the art forward, whether the rest of society appreciates their work or not. Many of them have not been recorded in history, but their work continues to improve and change our lives to this day. Ah, anyway, thank you for the work that you have done. And to the folks that I do not get called out, thank you as well. So, unfortunately, this means that Silicon Valley has been building artificial intelligence to be really good at lying, at appearing to be human and not necessarily disclosing its reasoning or where it comes up with ideas. This also means that uh, foundation models are incredibly good at hallucinating that they answers to things that don't have answers. A little bit like that guy who pretends to know stuff he doesn't in order to get a job or a promotion. I wonder who it learned it from. The truth is, we have a tendency to misremember, elaborate, and insist we are right. And if you work in data, you know garbage in, garbage out. I wouldn't want to work with somebody who was trained on the entirety of Reddit either, but here we are. These LLMs have been trained on some of our grodiest corners of the internet. They've been trained to repeat our own nonsense back to us in return for literal rewards. And they may repeat in misinformation, slurs, all of our worst qualities as well as our best. They do not question when there are holes in the record. We are far, in my opinion, far, far, far away from artificial general intelligence until these systems can reason about their impact and self-censor, much like a teenager growing up realizing that their parents are fallible and perhaps have only shown them one part of truth and then go seeking their own. Until that day comes, and artificial intelligence starts asking questions about its training data, I think we are still far away. But when it does come, I will say that they will arguably be smarter than we are. So how are we teaching? How are we teaching these foundational models? Well, there's a couple of different ways. There's unsupervised learning. This is my favorite. You can think of it as like sorting laundry. You give the model just the data and you give them the goal of finding patterns or structure, kind of a student learning without instructions. But then we have learning supervised learning. I was homeschooled. That means that my mother gave me some textbooks and some answer keys and said, go figure it out. And sometimes when the work was too tough for me, I would learn with the answer key open. If I couldn't figure it out on my own in 10 minutes, I would go to the answer key and I would work backwards from the correct answers to understand how to solve the problem. Turns out that's actually effective for humans and for models. You can think of this as giving your model input and its correct outputs, and then it can predict the outputs with new data. We actually will use that a little bit later. Now, then there's reinforcement learning, which is very familiar with training animals. I also trained animals on the farm. Learning through trial and error. You give the model an environment and a reward system. With humans, we have such a thing. It's called dopamine. Very easy to work with that. The goal is that the model will learn the best actions to maximize for rewards. Sort of like training a dog with treats. And then there's reinforcement learning with human feedback, the most expensive kind of training. In this case, you give a trained model, you take a trained model that you've trained on human raters of a set of data and examples of outputs. And you make a model that's trained to imitate how humans would rank responses, probably done with supervised learning. And you give the model a goal to create outputs that the human imitating model would prefer. So kind of like the voice, except instead of a human panel of rating the answers that the model is producing, they are also models. Well, but that's very good. How exactly is it learning? How exactly does it adjust to new input? Well, once again, uh, you'll hear a lot of game-changing and powerful and so forth adjectives in the media, but it's really just a lot of math. I'm a little disappointed. We had this math for a very long time. It turned out we just didn't have the compute to do anything good with it. But you look at it and you're like, really? Really? It took us this long? Okay, all right, sure. Anyway, let's take a look at the training cycle here. There's forward propagation, error calculation, back propagation, and then an update weights, biases, and parameters phase. And you repeat until you get the answer into an acceptable range of error. I prefer to work visually, so I'm going to use a diagram to go through this. So here we go. Boom. Forward propagation. Once again, we're looking at those layers. Imagine that retina we looked at earlier. In forward propagation, we pass the data forward and make that prediction. The little red box over here. Boom. That's the prediction, the output. Then we compare that prediction to reality or the expected results. Right, we calculate how much that prediction is close to it. Like, did you predict it was going to be a butterfly or did you predict it was a pigeon? Maybe if you predicted it was a dragonfly, that's really close to a butterfly. That's getting closer to that acceptable error range. Anyway, we calculate the distance between those. And we pass the error backward to discover which weights and biases impacted the prediction the most. And remember, we changed the weights in that retina so that the ones on the edge had less importance than the ones in the center. But if you were training something to react, for instance, predators in your peripheral, you might want the reverse weight and bias. Right. So then we perform gradient descent, which is where we go through and adjust the parameters to remove the error. And then you would repeat this until you got into an acceptable range of error. Each cycle is called an epoch, and you go until you feel like your results are good enough. Now, embeddings, these are a way to represent things, words, images, etc., as lists of numbers or arrays of numbers, as I think of them, so that AI can understand and compare them. Um, as I like to say to a learning machine, you aren't just a number, you're a collection of numbers. Here I'm representing some people that I care about a lot, and different parts of their personalities and characters on a scale. So, for instance, a scale from -1 to +1. Okay, so I am, for instance, very androgynous. My partner is very masculine. My best friend is a girly girl, and my sibling is a woodsy outdoors woman. So there you go. And you can see that I am autistic. My partner's pretty autistic too. My best friend is neurotypical, and my sibling, she probably has a touch of the ADD. And the athleticism, I'm a gym rat. My sister is an outdoor hiking fiend, she is always hiking on the weekend. All right. Now, in this case, you can kind of see that I have some major differences with my best friend. And how far removed are we from each other? Well, here's how you can envision this in kind of if you put each of those parameters in a three-dimensional space, this is where we would fall in a graph. I would be up here near my partner, my siblings over here, my besties down here. Now just imagine adding ever more dimensions to this graph, getting to n-dimensional space. That is how we're relating vectors to one another in this design. If it's a little hard to imagine, I can prove that I doodled this myself. Uh, I sometimes struggle with 3D representations on a 2D medium. Okay. Christoph actually gave an excellent talk on this topic yesterday about how the maths work, and I would actually recommend you go watch that in the DevMeo recordings. It's quite good. Now, now that we understand about where things being close together in nth dimensional space, meaning that they're closer related to one another, let's get back to some human visual metaphors and talk about vector databases and RAG, or retrieval augmented generation. So embeddings are like a set of coordinates. You can think of them, in this case, a set of coordinates in that n-dimensional chart. And you can think of them as books for this metaphor. I wrote my own embedding of me on a book. That's how much I put effort into this. And these coordinates, the sets of coordinates lives inside a vector database, which you might imagine as a library full of these books. A library where books about similar topics are stored near each other. Has anyone ever shelved books at a library? I have. The Dewey Decimal System is awesome. But the point is, every book has a place, and if you know the Dewey Decimal System, you can get it to it. It's kind of like it uses a split search algorithm. So anyway, uh, and here you can see that my partner and me, we're very close to each other. My bestie is a little further off, and my sister is as well. I think that's one-dimensional space, or no, that's two-dimensional. All right, and that brings us to retrieval augmented generation, which is, let's imagine it as your model's library card. So let's go back to tokens. Remember what we learned about tokens? They're pieces of input that you feed into a model. Models have token limits. And sometimes, the model, and you've got lots of information you want to reference, but your model just isn't going to be able to fit all of it into its context window. It also doesn't have any of that information. Maybe these are a big stack of recent newsletters. It was not trained on that information. This is all news about things that are going down around the world. How are you going to be able to reason about that news with your model? You can't just shove it into that context window. It won't fit through the door. When that happens, the first thing you do is you embed the new data into a vector database. You put all of those reference materials into your library where the information is stored near similar information. Now, so you've got all your newsletters, all your new friends in there, and you want to ask a question. I would like to go on a vacation with my friend. What are some good places we could go to? So that query gets logged into the vector database. It gets set up and it's near the other information. So next, the LLM can check out the related books by getting just the related embeddings needed to process the query in its context menu, context window. Hurrah. Phew, that was a tough one. I really wanted to explain RAG to the layman because I felt that it was being proposed as a solution to far too many things. Let's recap. While machines learn from backprop, humans learn by spaced repetition. That means quizzes and reviews. So, you have witnessed our evolution from narrow AI towards AGI. You have seen that LLMs do a great job of mimicking intelligence, but they are recombining things we fed them in ways that please us. You have seen how layers of math called neural networks underlie deep learning and know that backprop is where that learning happens. You've also learned that you are a collection of numbers, at least when it comes to AI, and that you can use embeddings to train a model to understand anything. If you can assign a number to it, it can be reasoned about. And that the LLM can just get the information it needs to reply to a query using the RAG method. You can find all of my socials, but I also blog quite a bit about the agentic web. Yeah, and hit me up if you'd like to talk about any of those things. Don't forget to go vote. Unlike Claude here, I need human feedback to continue to give better and better talks. So thank you very much. Question. That is a good question. I actually don't have the answer to why Claude has only a fraction of the context window openings that Google does. I'm also not convinced that bigger and bigger context windows are the answer. I think it makes it easier for chat conversations to have a huge context window, but when it comes to production, to production deployment, you're probably better off implementing something more like RAG that uses data a little bit more efficiently. But if anyone else has an answer to that, this is a learning space. Please answer, and we will share here. So, so the context window size is determined by how many resources you have available to keep it open. It does. It would also explain why Google is pouring. It's the Walmart effect. Uh, where you make something very attractive to users by offering, by taking a loss to make it so. If it takes more resources than your competitors and you run a loss to have a larger context window that makes your model more useful to the everyman and you sell more of it, you can drive out your competition and work on either lowering the cost or making the context window smaller in the future. God, I love capitalism. Any other questions? I'm so glad I learned something new in this one myself. All right, go get your lunch. Go get your lunch. It was lovely chatting with you.